beyond student in computer science. I'm going to discuss quantum computing. Quantum computing is a good field that is set to redefine our world. Okay. Hello, my name is Mike Mukiibi. I do computer science. Yeah. I'm going to talk about quantum computing. Quantum computing is a field that is going to redefine how computing is. However, we may ask what is the difference between traditional computing or classical computing and quantum computing. Now, to actually approach this new paradigm of computing, we shall talk about computable problems, what is computing. So, we shall be talking about pivot as a new problem. So, to this, we shall say that a problem is a problem at all determine its solution in polynomial time. This is traditional algorithm computational complexity. If you know that I can determine the location of an item in a list in n operations, that is a P problem. Searching is a P problem. Say binary search can determine the location of an item in log n time. That is still under what? That's a polynomial problem. That's a P problem because you can find a solution in polynomial time. However, what's an NP problem? On the other hand, an NP problem is that kind of problem for which you do not have a straightforward solution in polynomial time. Like you're not sure. NP stands for deterministic polynomial time. So how does this relate to quantum computing? So first of all, it is known that first of all, when I try to relate this to quantum computing, I see that there are particular problems that can be solved in polynomial time, and then there are those that cannot be, that it is not known whether they can be solved in polynomial time. Now, in our discussion throughout the semester, I'll be linking this discussion between applications of quantum computing, especially cybersecurity, particularly cryptography. So it is alleged that quantum computers will actually at some point be able to actually break internet security. So throughout the semester, we shall be exploring that whole idea that is impossible. And today, I would like to talk about so quantum computing extends this discussion further by further splitting the, okay, the assumption is that an NP problem is hard, and we could as well just focus our design of, say, if you want to, our design of encryption around an NP hard problem, rather an NP problem. Because if I told someone can actually, if I told someone can easily get your password, like if I told that was easily computed in polynomial time, then that would actually be, then that means your security will be breakable. However, it isn't always the case that when you're actually designing secure functions in cryptography, it isn't the case that they are always NP hard. Rather, it isn't always that they are NP problems because of how they just naturally arise. However, quantum computing introduces a subclass of NP problems called computational boundary error quantum problems. So we shall be looking at how different algorithms are used to actually break purported hard problems. For example, if you look at an algorithm called RSA, it is used throughout traditional communication. WhatsApp uses end-to-end encryption. And end-to-end encryption is focused on elliptical cryptography. So quantum computers, the algorithms that actually have been broken to break many of the security assumptions in many of those encryption encryption algorithms. So throughout this thing, I'll also be looking at how we can actually visualize the different algorithms that can be used to mainly that are being used to possibly break current encryption algorithms, and then we shall also be working on a project to simulate a quantum computer on a classical computer using just a few using a few bits. If I don't this right now. So yeah, I'll be explaining the rest of the document that I'll share. Thank you.